Hello students, in the series of lectures in the subject VLSI technology, today we are starting with lecture number 5, that is silicon shaping. So, as we all know that silicon is a hard, brittle material. Uh, the most suitable material for shaping and cutting silicon is basically your diamond, industrial grade diamond. Although for low cost purposes, sometimes we can use silicon carbide and AL23 also. So in this lecture, we will discuss major shaping methods. So in the previous lectures, we understand how we get silicon ingots. Okay. So from silicon ingots to the polished silicon wafers, there are certain processes, certain machining operations. There are mechanical processes as well as there are chemical processes. So in this lecture, we will discuss all these processes so as to obtain polished silicon wafers from silicon ingots. Okay. So here in the diagram, you can see that uh, these are the silicon ingots that are formed. Okay. So from these silicon ingots, we have to get the polished silicon wafers. Okay. So the very first shaping operation includes basically the removal of seed and tangents from the ingots. Okay. So basically, the silicon ingots looks like this. Okay. So there, these ends you can see here, tangents you can see here. There is certain seed and also there. Okay, because you have seen in seeded process that we used a seed crystal on which the silicon was grown. Okay. So that is the seed end and this is the tang end. So first of all, these two ends are removed. Okay. So now in this process, the portion there is certain resistivity tests are also there. Okay. In order to measure the resistivity, the portion of ingots that fail this test, okay, are also cut off. Okay. So these rejected ingot pieces, okay, can be used as a metrological grade silicon, and from that we can obtain electronic grade silicon by repeating the same processes, okay, that we discussed in previous lectures. Okay, so now cutting is done using a circular saw. So we use a circular saw in order to cut the seed and tang ends. Okay, now after this step, you can see that there are certain irregularities on the surface of that ingot. Okay, so in order to remove these irregularities, okay, we use surface grinding method. This is the next step in silicon shape. Okay. So it defines basically the diameter of material of which diameter wafer we want. Okay. So according to that, this is the schematic diagram of a diameter grinding tool. Okay. So here you can see that this is the ingot. Okay. It is rotating in anti-clockwise direction, and along with that, a diamond cup wheel also rotates in clockwise direction. Okay. Now, as per the requirement of the diameter of the buffer that we want, this tool, diamond cup wheel tool, can move here. Okay, as per the required diameter of the ingot. Okay. So as you can see that when this will move clockwise and this move anti-clockwise, we get the grinding of the surface as well as we get the desired diameter. Okay. Now After diameter grinding, so there are certain flats that are assigned to the wafers. Okay, so these flats are basically the major flat is known as your primary flat. Okay, so largest flat is called primary flat, and second one is called secondary. So secondary flats are also there. So these flats basically tell two things. Okay, one is what is the doping type of wafer, and another one is the orientation of wafer, whether it is a 100 or it is a 111 condition. Okay, as you can see that for 111 N type silicon wafer, okay, uh, primary flat, and this is the secondary flat, and for the angle between primary and secondary flat should be 40 degree. Okay, so by seeing this type of wafer, we can tell that this is an N type silicon. Okay, with orientation 111. Now for 111 P type, there is only primary flat here. But now if the angle between primary and secondary flat is 180 degree, then it is a 100 orientation type. And if the angle between primary and secondary flat is 90 degree, then it is a 100 type condition. Now, uh, if the diameters of the wafers are larger than 8 inches, okay, so these do not have flats. If the diameter of wafers are less than that 8 inches, 6 inches are there, 4 inches are there, then we use this kind of flats. If the diameter is more than that, that is 8 inches range, then we do not use these flats. Because if we use these flats, then we would have certainly lost pretty much amount of uh, material from the wafer. Okay, so for this purpose, we use notches. Okay, so these are the notches that we use, and here subscribed identification number is printed, and according to the nomenclature of that, we can identify various things on this. Okay, so by doing this, a very less amount of silicon is removed from here. Okay, so this type of identification is used if the diameter of the wafer is more than or equal to 8 inches. Now we use ingot slicing. Next step is your ingot slicing. Okay. So silicon is obviously very hard. Okay, so special tools are needed to slice the ingot into smaller wafers. So slicing is very important. Okay. It determines basically four parameters, that is surface orientation, wafer thickness, taper, and form. Okay. So as you would know that the properties of silicon, mechanical properties of silicon differ with the orientation. Okay. Wafer must be sufficiently thick enough to support an arm weight without cracking. Okay, during handling. So what should be the minimum thickness? Okay, of wafer. So that this is the formula by which we can find the minimum thickness of wafer. Okay. Now there are two slicing methods by which we can slice silicon wafers. We can slice silicon ingots. First one is ID saw and second one is wire saw. So ID slicing is the common mode of slicing ingots. So here, what is done? Saw blade is a thin sheet of stainless steel, okay, of approximately 325 micrometer thick with a diameter wanted in a ring. Rotation speed is around 2000 rpm. Okay, so here the ingot is stationary and blade is moved relative to the stationary ingot. Okay, the operation is continued until the step is complete. Okay, now here ID saws basically cut to one wafer at a time. Okay, and and this so is water cooled to avoid excess temperature generation. This is the simplest process of slicing the silicon inputs. Okay. Now, second method is a wire saw. So, wire saw, it takes several hours to cut through a silicon ingot. Okay, but various so many cuts are imparted on the silicon ingot simultaneously. Okay, so now uh, in this process, entire silicon ingot is wafered. Okay, in a single operation. Okay, while in ID saw method, we were getting a single wafer at a time. So this is the very simple diagram of a wire sway. So here is the movement of ingot. Okay. Now these are the wires. Okay, and these are the rollers that move clockwise and as well as anti-clockwise directions. So as these move downward, these wafers are hit according to that. Okay. So as many numbers of wires are there, so as many wafers we get. So this is the industrial implementation of wire jaw machines. Okay. So that are interesting. Now, after the slicing method, there is one another method that is called mechanical lapping of wafer slices. So the slices we obtained basically after any of the two methods, ID so whether it is the wires. Okay. So these methods basically produce lot of unevenness on the surface of wafer. Okay. And mechanical polishing is necessary to remove this surface irregularities. Okay. So for doing that, wafers are placed on a lapping pad. Okay. And fine Al2O3 aluminum powder mixed in glycerin is applied under constant pressure. So here is the important thing here. The thing is that wafers are placed in a lapping pad. Okay. So this is the lapping pad that you can see here. Okay. And a fine Al2O3 mixed in glycerin is applied under constant pressure. Okay. So this is a two-side lapping method. Okay. So here you can see there is one side lapping method as well as there is two-side wet lapping method. Okay. So this basically removes uneven shapes present on the surface depending on the powder fineness. Next is age profiling of slices. So after mechanical lapping process, okay, wafers are separated and are taken for age counting. Okay. Now up to this process, mechanical lapping of wafer, the wafer formed have basically sharp edges. Okay. So in order to convert the sharp edges to round shape, okay, we use this edge profiling method. So in this edge profiling method, you can see that there is a timing cutting tool here. Okay, and this stand rotates basically like this, and this cutting tool also rotates. So we get the round shape by this method. Okay, so this is the chemical. After that, chemical aging and mechanical damage removal is done. Okay, so the previous described shaping operations leave the wafer surface and edges damaged and contaminated with chemicals and fine particles. Okay. So all the previous methods were basically your mechanical operations that were performed on the silicon ingots to get silicon wafers, and by these mechanical processes there were several um, damages, contamination that can take place on the surface. Okay, and certain chemicals can be contaminated on the surface of wafer. Okay, so these mechanical damages are roughly around 10 micrometer deep from the surface. Okay, so certain chemical bleaching processes are done so that these can be removed. Okay, uh, these mechanical damages are basically uh, to the 10 micrometer deep from the surface of the wafer, but for the sake of safety, 20 micrometer thickness from the surfaces by chemical etching process. Okay. Now the chemical etching involves a combination of hydrofluoric acid, nitric acid, and acetic acid. So this is the reaction that takes place here. Okay. So what is the role of that hydrofluoric acid? It basically dissolves the product. Okay. Acetic acid does nothing in the reaction, okay, but only dilutes the system, okay, so that the etching can be better, okay. So it also improves the silicon surface and leaves it shine. Now, this is the chemical polishing for planar wafers. So this is basically a final step in silicon shaping. So depending upon the application, polishing is carried out on one or both sides. We can do polishing on one side, we can do polishing on both sides. Okay. For the sake of VLSI and VLSI applications, polishing of one side is sufficient. But for MEMS applications, that is micro electromechanical system applications, polishing of both sides is required. Okay. Now, what is the purpose of this polishing? So, purpose of polishing is to provide perfect and smooth surface on which device can be photon. So here, what is used? So here we are using a polishing pad. Okay. It rotates continuously, and we use a slurry. Okay, here. So that is deposited on the polishing pad. Okay. Now, as the polishing pad is rotating, the wafer is attached to this polishing pad, and certain chemical reaction takes place here. Okay, so that polishing is done. Okay, so these polishing pads are made of basically artificial fabrics such as polyester felt, okay, or you can use polyurethane laminate, okay, and they will not contaminate the polishing process. The slurry here is used as a colloidal suspension of silicon dioxide particles, okay, typically 10 angstrom in diameter, okay, in an aqueous solution of sodium hydroxide. So by this we can use chemical polishing. Now after chemical polishing, wafers are chemically cleaned with acid-base or solvent mixtures of residue from so if any glue layers are used for single side polishing, the residue is removed with proper solvent, dissolving the glue. Now there is final cleaning and inspection process. So final cleaning of silicon wafer is carried out in different stages, such as the standard Piana cleaning based on a mixture of sulfuric acid, hydrogen peroxide, and RCA cleaning steps. So this was the final cleaning steps before the packaging of your silicon wafer. Okay. So these are the method, these are the steps that were used for your silicon shaping. Okay. This is all about this lecture.